Throughout this tutorial, we'll be looking at the various stages of a star's life. But something that's been missed from the syllabus that I think is really important you understand is where the star is born. So we'll start this tutorial with a little bit of pre-topic knowledge looking at the nebula.
Now, how did it all start, or how did our sun all start to allow us to have life? Well, the sun and all stars were born in a nebula. A nebula is a massive cloud of gas and dust, and you can see that here on the right. And what this gas and dust does is it's pulled together by the force of gravity, and it starts to get more and more dense. And when it gets more and more dense, it gets hotter. And when it gets hotter, a protostar forms. A protostar is just before the star becomes properly born. Then, temperature and pressure of this gas and dust being pulled together gets high enough to allow hydrogen nuclei. Now, hydrogen nuclei is just basically a proton. And another hydrogen nuclei, another proton, to fuse together to become helium. And once that happens, a star is born. The star sits on the main sequence and is a star for a very long time. And what happens during this fusion reaction to justify it being a star is fusion gives out a huge amount of thermal energy, and that allows the star to radiate.
Which leads us nicely into fusion. We've already studied radioactive decay, we've already studied fission, and from those studies we've learned how to calculate the amount of energy released from those reactions. Now we're going to look at fusion. We'll look at how much energy is released in fusion, and we'll start to look at its role within stars. Well, it's helpful to know what fusion actually is, and the very small, easy to learn definition of fusion is that small unstable nuclei can become more stable by fusing together into larger nuclei. When we're looking at very small nuclei, we're looking at things like hydrogen, helium, lithium, and these all sit very low down on the average binding energy per nucleon scale. And they become more stable by fusing together and climbing up this curve. The energy released per nucleon in fusion is much greater than that in fission. So if we could find a way to harness nuclear fusion, we'd create much more energy and generate much more electricity than we would by fission. And we wouldn't need any radioactive waste products. So nuclear fusion is a very desirable goal for physicists, with the potential to save the world. If we head back to the graph, I have said that the energy released per nucleon in fusion is greater than that in fission. And that's shown by looking at this graph. You can see that the steepness of this curve here compared to the steepness of the curve there means that more energy would be given off by a fusion than it would be by a fission, because the change in energy climbed by a fission is less than the change in energy climbed by the fusion. On the subject of energy, there is a mass defect between the reactants and the products of a fusion reaction. The missing mass is converted to energy according to E equals mc squared. And where have you heard that before? We've heard that in fission. This time though, the balanced equation looks slightly different. On the left-hand side, we'll have two smaller nuclei. On the right-hand side, we'll have a larger nuclei, a neutron to balance it out, and lots more energy. There's not that many fusion reactions possible, and this is one of the most common reactions that you'll find. I'm not asking you to memorise this reaction at all, but it is the most common, and I'd be happy for you to pop that into your notes as an example of what a fusion reaction looks like. Just like we did with fission, it's desirable for us to be able to calculate the energy released in a fusion reaction. And we have an example question here. It says the nuclear fusion reaction is shown below. Calculate the mass defect in the reaction and hence the energy released. Let's calculate that mass defect. That gives us a value of mass defect as 0.02895 U. We know that 1 U is equivalent to 931 mega electron volts. So we simply multiply that by that to give us the energy that's out. And the energy released in this equation is going to be 26.95 mega electron volts. Lots and lots of good energy. Obviously, there's a problem when you try and push two nuclei together. The problem is that both of those nuclei are positive. That means there will be a huge, massive, repulsive Coulomb force, and that needs to be overcome. In order for fusion to work must be done on those nuclei to overcome that massive repulsion. We've previously looked at calculating the Coulomb repulsive force, and we found that the repulsive force between two protons was in the order of magnitude of 57 newtons. So we need to provide enough energy to overcome this 57 newtons. I know 57 newtons doesn't sound a lot to you, but we're looking at this microscopic scale. It's huge. And we've already used this relationship to calculate that number. Let's look more into those numbers, right? So we use that relationship of the kinetic energy transferring into electric potential energy. And I want to know just how much energy is required to do that. And by using that simple equation, we can do just that. We can work out that 1.15 times 10 to the minus 13 joules of energy is required to fuse two protons together. That energy is all provided as kinetic energy. And we know from our studies of thermal energy that kinetic energy is related to temperature using this relationship. If we rearrange that, we can find out the temperature required to fuse two protons together. And the temperature required is huge. If we ever wanted to carry out fusion on Earth, we'd have to create these temperatures, but we'd also have to create a very high density, which is very difficult. And we'd have to sustain it for a long time. Two of these things are not actually impossible. We can create temperatures of this magnitude, and we can create densities of this magnitude on Earth, which means we can sustain fusion on Earth. We're nearly saved, right? But what we can't do is sustain it for long enough to allow the heat released from that fusion reaction to then start generating power. Believe me, we've tried. In the UK, we have something called the Joint European Torus Reactor. It's called JET for short. They started building that back in 1978, a long time ago, and it's still going strong and it's still developing. What it does is it investigates the potential of fusion power as a safe, clean and virtually limitless energy source for future generations. It's going to solve our problems. And it looks like this. It looks like a giant donut. It uses magnetic fields to confine plasma long enough to maintain fusion. By using magnetic fields, it means the plasma doesn't physically touch any surroundings. Because you can imagine if plasma is contained within a metal box, that metal box is simply going to melt. So magnetic fields are used to contain the plasma. There are only a few types of fusion reactions that are actually possible, and the most efficient type is the reaction of deuterium-tritium fusion, and that's the one that's used inside this jet reactor. And then the very clever scientists who have developed this jet reactor have used a myriad of different types of magnetic fields to interact with each other to make sure that this all stays contained and works. And there's a heating magnet in the middle. You don't need to know this. I just thought you'd find it interesting. I thought you'd find it interesting because there are huge amounts of pros related to generating power through nuclear fusion. The pros are there's no emission of greenhouse gases. We'll never run out of fuel. We've got loads of hydrogen and helium. There's no radioactive waste. It's an inherently safe system once it's set up. And actually, this should go over here. There are cons. The cons are the plasma needs to be heated up to temperatures of at least 100 million degrees Kelvin. The heat energy created from the reaction needs to drive turbines, which is difficult in itself. Plasma must be contained without melting the walls of the vessel. That's another engineering problem. There are byproducts. There are things that are created from a nuclear fusion that need to be removed. Another engineering problem. and the reactions can only be maintained for a matter of seconds using the current technology. Another engineering problem. So we have lots of engineering problems here that have yet to be solved. However, if these can be solved, our worries are over. We'll have boundless energy with no carbon emissions and no fuel problems, allowing us to be politically safer and to be environmentally safer. Nuclear fusion is the future if we can get it right. We need some engineers. Off you go. Go and be an engineer, please. Okay, head to your revision note template. Draw the fusion diagram that I showed at the beginning. Define fusion. What was that one sentence at the beginning that defined fusion? And then note down the pros and cons for fusion as an energy source. Finally, complete questions 1 to 3 in knowledge questions. Now we know everything about fusion, let's take it on to stars. So we've talked about a nebula and how that generates a protostar. We recognise there was a role of fusion in doing that, so we talked about how to get fusion going, what the conditions necessary for fusion are, and the energy released in fusion. The next part of our journey looks at main sequence star and gaining equilibrium in that main sequence star.
And once we've got this nuclear fusion going, the protostar turns into a main sequence star. And that's what our sun is right now. Our sun is a main sequence star. What does that mean? Well, it radiates an enormous amount of energy into space in the form of electromagnetic waves. And what electromagnetic waves do we feel on Earth from our sun? Well, we feel heat, which is infrared. We see light, which is visible light. If you have ever sunbathed, you might get sunburns, so we'll have UV rays. All these electromagnetic rays are being given out by the sun, and they pass through space to us, to Earth. And the source of energy, the reason that the sun can provide these electromagnetic rays is through nuclear fusion. And nuclear fusion causes radiation pressure. That means it pushes the edges of the star out, and that's represented by these green arrows here. Radiation pressure pushes the outside of the star out, but gravity pulls it back in again. And as long as gravity balances radiation pressure, the star is in stellar equilibrium and it is a main sequence star. Now, the good news for us is that happens and stays that way for several billion years, a long time. And we believe that our star has a good few years in it yet, so I don't think anyone has to worry. As I said before, our sun is a main sequence star, and what that means is it's currently fusing hydrogen into helium. And it will stay that way for a long, long way. But what happens next?
Head to the other notes section in your revision note template and note down some facts about the nebulae and the main sequence stars. In particular, I really want you to focus on the balance between the radiation pressure outwards and the gravitational collapse inwards, keeping that a nice stable star.
In the last set of learning objectives, I said rather ominously, what happens next?
And I'd like you to indulge me, because before we can even look at an HR diagram, we have to understand the life cycle of a star, and we have to understand how we classify stars. I promise we'll get to HR diagrams soon, but we have to go on a little journey first, and it's quite an enjoyable one, so let's go.
Well, after it is a main sequence star, and we've got this diagram on the left, and I'd like you to kind of imprint this diagram in your brain. We are, of course, going to draw it in the common diagrams section of your notes in a moment, but this diagram basically tells you the life cycle of a star. And we're interested in this side of it, because that's what's going to happen to our sun. If you can read diagrams, you can see that we're a main sequence star just now. What happens next is it turns into a red giant. Well, what is a red giant? Let's have a look at this picture here. This is not a photo, obviously. This is a diagrammatic representation of a red giant next to the sun. But that is what our sun's going to turn into. Eventually, our sun will run out of hydrogen and it won't be able to fuse hydrogen anymore. What it does is it expands, as you can see, it's massive, and it cools down. And when it cools down, it begins to appear red. So guess where the name red giant comes from? It's not that inventive, is it? It looks red and it's massive, red giant. But what takes place inside the core is fusion of other elements. So inside here, there's still fusion of other elements. What that means is helium might be fusing into lithium and all sorts of things might be happening in there. Oxygen and carbon and nitrogen will all be fused inside the core. But the outside of the star will get big and it will cool down and look red. So after it's turned into a red giant, it goes the exact opposite and turns into a white dwarf. Now you can see the relative size of a white dwarf in comparison to the Earth. So our sun has gone from the size of the sun, which is much bigger than the Earth. It turns into something much, 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 much bigger than the sun. And then eventually it becomes unstable and it throws off its outer layer of gas and dust. So that red giant just loses its temper basically, and it throws a tantrum and it throws off all its gas and dust, and all that's left behind is this very hot, very dense white core, and it appears white because it's much hotter. And this white dwarf is what will be left of the sun after it's become a red giant and gone through that phase. Then, I'm sorry to tell you, it just kind of fizzles out and it becomes a black dwarf. So the white dwarf cools down, it emits less energy, and it's no longer visible because it's got low energy radiation. So where our sun currently releases, and we talked about this earlier, infrared radiation, visible light, and UV, it will start to give out radiation, but radiation that's much less energy and you can't see. So it would give out, at this stage, microwaves and radio waves, and they're at the lower energy end of the electromagnetic spectrum, and it's just no longer visible. It's just a nothing in the sky. So I'm really sorry to tell you, but what next is for our sun? Our sun will become a red giant and it will swallow us up. The Earth will be swallowed into the red giant. Then it will throw a tantrum and throw everything off and become a white dwarf, and then it will fizzle out into a little black dwarf as we've seen here. Can you please go to your common diagram section, and can you draw the diagram that I want you to imprint in your brain? It's here. Draw that into your common diagrams section, please. And if you need to note down little things about each section, red giant, white dwarf, black dwarf, just annotate it with a couple of little notes on the side. Would you believe me if I told you that our sun is actually really tiny compared to other suns? Okay, it's not really tiny, but there are other stars and suns that are much, much, much bigger. And I'm interested to know what happens to those stars that are much more massive than our sun. So the diagram we imprinted in our brains before, it's still here. But after the main sequence star, if your star is much bigger than our sun, it takes a different path. And you can see that path comes down here. The path it takes, and again, we're not very inventive astrophysicists, it turns into a red supergiant. It's much bigger. So a large star that's much bigger than our sun becomes a red supergiant, and it's the same thing. It's because the star has run out of hydrogen, so it can't fuse hydrogen anymore. So it expands and cools and appears red. But again, as before, fusion of other elements still occurs in the core. So we're creating things like carbon, oxygen, nitrogen, all those things inside the core of the red supergiant. But this is where it gets interesting. Because after it becomes a red supergiant, it starts to glow brightly again and it contracts. So this supergiant gets really bright. And when it's really bright, it contracts all the way down. So it goes like this. It contracts into a tiny, tiny, tiny hot, dense core. And inside that hot, dense core, no fusion can take place because there's already iron fused in that core. And iron is the biggest element that can be created through nuclear fusion. So once they've got to the fusion of iron and they can't fuse anything else, it goes nuts and it explodes. And during that explosion, all the elements bigger than iron, like uranium, they are formed during this explosion. And these elements are all thrown into space. And when they're thrown into space, they join in to the nebulae and the planets, and everything else is made out of those elements that have been thrown out by supernovae. And guess what? Guess what the Earth was made of? It was made of the remnants of a supernova. And here we are. You are made from stars. You are made from a massive explosion of an older star, throwing out all of its elements to turn us into who we are today, complete and utter stars. Now, I'd like to end the course based on that note, but there's still some stuff happening, so let's go and see what happens next. We've done the red supergiant, we've done the supernova. What else happens to massive stars bigger than our sun? Well, there's two paths here. It can either become a neutron star or a black hole. Let's have a look. A neutron star is a very, very, very dense core of star. It's tiny, but extremely heavy. And to give you some idea of this neutron star, if you were to hold a teaspoon of neutron star, I think the statistics are it would weigh the same as the sun, or it would weigh the same as the Earth, or something ridiculous. But it's the most dense material, apart from a black hole, known in the universe. And it's really dense because neutron degeneracy pressure exists inside the neutron star. You don't need to know that. That's not important. Well, it is if you go to sixth form. But all you need to know now is after the supernova, it either becomes a neutron star, which is very dense and small, or it becomes a black hole. Now, a black hole was first predicted by Albert Einstein back in 1916. And he called it a black hole because he said it's so dense that even light, which doesn't have a mass, could not escape it. And we believed in the existence of black holes for a very long time, but there was never any proof because we could never actually capture any images of it. And actually, very recently in 2019, scientists believe that the first image of a black hole was taken, and I put that image down there for you there. This is believed to be the image of a black hole. Now, you know what science is like. Scientists make observations, they make theories, and they're either proved or disproved. And in this case, we think this is a black hole, so it could be proved. But science might come along, something might come along and disprove it or come up with a better idea. So if you were to ask me, do black holes exist? I don't know if I could give you a yes or a no answer. I'll be honest with you. They're so far away and such difficult concepts to really prove. I'm not sure if a black hole exists. Right, let's head to our revision notes. We've already got the common diagram in here. But what I'd like you to do is annotate that common diagram, so this side, just to give little notes about the things we've learned about a red supergiant, a supernova, a neutron star, and a black hole. Don't overdo it, just stuff that you might need in the exam. Okay, here's a Hertzsprung-Russell diagram. And what it does is it organises stars based on what their temperature is. And you can see we've got a cool temperature here and a hot temperature there. And it organises them in terms of how bright they are. So we've got very bright and not very bright either. That's not very good maths, or that's not good physics words, is it? But the brightness increases that way. And if you start to plot the temperature and the luminosity of various objects in the sky, you get patterns that form. And the patterns that form are shown in this Hertzsprung-Russell diagram. We find that main sequence stars come along a sort of sweep along the centre of the Hertzsprung-Russell diagram here. So we'll just do that. That's where the area where you'd find main sequence stars. You'll remember that I told you our sun has a surface temperature of 5,800 Kelvin.
and it's got a luminosity of 1. So we'd find our sun here on the main sequence stretch. Down here are the white dwarfs. So after our sun has stopped fusing hydrogen to helium, it'll become a white dwarf. So it'll go down like that. And the white dwarfs rolled in there. They've got a high temperature and a lower luminosity. The red giants are cooler than most of the main sequence stars, and they're not as bright, so they're brighter, so they head up here. Red supergiants up here, and blue giants, very hot, very luminous here. Now, what would you be asked to do? Well, it says draw the main components of the Hertzsprung-Russell diagram. So you'd have to be able to draw a graph that looks like this. You'd have temperature, and you'd have to say cool here and hot here. And then you'd have luminosity there. And then what you'd want to do is you'd be able to just draw sort of areas. You want to say that's the main sequence. Red giant. Red supergiant. Blue giants, very hot, very luminous. And white dwarfs down here. And you can recognise that as a sun goes through, or as a star goes through its life journey, it will move on the main sequence. So our sun would start here, and then it will turn into a white dwarf and go there. Oh no, it won't. It will go up to the red giants and then down to the red dwarfs, like that. If you had a much hotter, bigger sun, so we have a star here, it will go to a red supergiant first, and then it will carry on its journey to become a supernova from there. So the stars don't stay exactly in the same region all the time. They move throughout the Hertzsprung-Russell diagram depending on what stage of life they are. So, common diagrams. Let's go and draw our Hertzsprung-Russell diagram. Memorise that, okay? So to measure distance in astrophysics, it's not that easy. It's not that easy because you can't just take a ruler and put your ruler at one end of the Earth and then, measure the distance to the nearest star. There's no physical way of making measurements of distance in astrophysics, and that makes things quite tricky. Okay, so we have to come up with ways of finding distance. And none of this is rocket science, although it is. We have to make it as simple as possible. And the reason it's simple is because people discovered these methods years and years ago. And one of the methods of discovering what the distances are in astrophysics is using something called parallax. And I'd like to talk you through that today. And specifically, we want to define the parsec, and we want to describe the method used to determine a distance to stars using stellar parallax. We want to understand the limitations of this method as the distance increases. First of all, we'll start with learning objective. Describe the method to determine distance to stars using stellar parallax. What we have here is a slightly basic diagram, but if you look at the diagram down here, you can see the sun is in the middle of that circle, and what the Earth obviously does is it orbits the sun, and it takes a whole year for it to orbit. At one stage in June, say in the summer, we're at the top end of the sun, or at one extreme of the orbit of the sun. And 6 months later, we're at the other side of the sun in terms of the orbit. And that fact is really useful for us determining distances. And I'm going to come back to me so we can talk you through why. Okay, so what I'd like you to do is I'd like you to put your finger out in front of you and look at something really far away. You can't see what's behind my computer, but I'm looking at my wall and there's 2 pictures of my kids on there. Okay, so I close one eye and I look at where my finger is in relation to the distant pictures of my children. And actually looks like I'm picking my daughter's nose in this picture. Okay, because my finger is right on her nose. And then I open the eye and close the other eye, and I look, okay, where's my finger in relation to those pictures? Well, my finger is now at my son's hand. It looks like when I change eyes, the position of my finger changes. Now, we both know that the position of my finger stayed exactly still, but the relative position of it appeared to be different. So if we go back to the slides, the same can be done when looking from the Earth, but instead of closing each eye, we're actually at a different position in the Earth's orbit around the Sun. So in June, if you look at a star, the foreground star, which in this example was our finger, and if you look at that foreground star in relation to distant stars, you see it in a certain position. You wait 6 months later, look at the same star or the same finger in relation to the other side of the Earth's orbit, and it looks like it's in front of a different star. Okay, so that change in relative position means we can work out the difference in angle. So if you've got a really good telescope, you can say, well, the angle in June was here, the angle in December was there, and you can work out what that angle is using your telescope. And then all we have to do is use a little bit of trigonometry to work out what the angle between the Earth and the star is. Because we've got the angle, we can see a right angle triangle, and we can use trigonometry. And this apparent motion is called stellar parallax. So all parallax is the appearance of something being in one position and another position, and depending on the line of sight. Now, before we get down into the trigonometry of this relative positioning, actually making a formula for it, we have to understand what something called a parsec and an arc second is. And one of the things you need to know is the definition of the parsec. An arc second is an angle, which is a weird thing. I know it's a weird definition of an angle, but like an arc second is an angle. And that angle is equal to 1/3600th of a degree. So it's absolutely tiny. If you think of a degree and then do 1/3600th of that, then that is an absolutely tiny angle. Okay, so an arc second is an angle and it's very, very small. An arc minute is an angle and it's 60 times greater than that. A parsec is the distance of a star that has a parallax angle of 1 arc second using a baseline of 1 AU. Let's go back. In the previous slide, we looked at this idea of June to December, going, the orbit of the Earth and so on. The baseline is the line between June and the Sun, or the Sun and December. That's the baseline. And you want the biggest baseline possible to get the most accurate value of parallax. So the baseline is this vertical line here. The parallax angle is the angle that you see is subtended between the Sun, the star, and June. So it's half the angle that you would calculate when making your measurements. So if we go back to the definition of parsec, the parsec is the distance between the star and the Sun that of a star that has a parallax angle. So this angle subtended here is 1 arc second, or 1 divided by 3,600th of a degree, using a baseline of 1 AU. Now 1 AU is 1 astronomical unit, and that is basically the distance between the Earth and the Sun. 1 parsec, if you were to do the maths, the trigonometry maths, which I'll tell you about in a second, 1 parsec is then equal to 3.08 times 10 to the 16 metres. And that is shown in your data booklet. Don't need to memorise that. Okay, it's just a unit of length, and that's what it is in metres. So the parallax method, let's look at that in a bit more detail. So we've got another idea of this idea of parallax method. We've got the 1 AU that shows between the Earth and the Sun. You can see it's a right angle triangle. The distance between the Sun and the nearby star is D, and the parallax angle P is given as a P. Okay? we can calculate the distance because it's a right angle triangle. We can use SOHCAHTOA, like sine equals opposite over hypotenuse and so on, trigonometry, to find what D is. Now, I've told you that the angles are really, really small. And in astrophysics and in maths of any sort, when you have a very, very small angle, you can use something called the small angle approximation. And it really simplifies all your calculations. And what it effectively does is it simplifies your formula for finding out the distance to a star down to something extremely simple. You can find the distance to any star within a range using D, which is distance in parsecs, equals 1 divided by P, which is the angle in arc seconds. It couldn't be any easier. As long as you have both those units in the right units, then everything becomes really simple. So let's take an example. A star has a parallax angle of P is 0.723 arc seconds. What is the distance to the star? So the angle is already in arc seconds. We'll say D is equal to 1 over P. So 1 divided by 0.723 is 1.38 parsecs. Simple as that. Now you might be asked to then give it into meters, and in which case you have to do 1.38 times 1 parsec to meters, but that's given in the data booklet and it couldn't be simpler. So this distance, once you've got it in parsecs, can be converted to meters, light years, and or AU, astronomical units, by using the data that's given in the data booklet. It can't get any simpler. Now, is there a problem with parallax? Well, of course there is, because there's limitations. If you look at the diagram below, you can see a close star has a very obtuse angle. It's an angle that would be easy to determine. But there aren't that many close stars. The nearest star is something like 4.26 light years away. Actually, we're never going to get a big obtuse angle like this. The stars that are further away, the angle gets smaller and smaller and smaller and smaller and smaller and smaller. In fact, the angle can be so small that you can't even measure it. So the further away a star gets, the parallax angle gets so small that it's too small to measure. And that happens when a star is around about 100 parsecs away. So any stars within 100 parsecs, you can use the parallax method to measure its distance. Anything beyond 100 parsecs, you have to use a different method of measuring distances. And that is covered in the IB syllabus as well. Now, interestingly, if you're using a telescope on Earth, because of the atmosphere and the distortion due to the atmosphere, you can actually only measure stars using the parallax angle up to about 25 parsecs. If you use a telescope that is beyond the Earth's atmosphere, so using a satellite of some sort, then you can measure stars that are further away because the atmosphere doesn't distort the position of the star. So you can find the distance of stars up to around about 100 parsecs if you use a telescope that is outside of the Earth's atmosphere. So whilst it's a really easy and simple calculation to make, it only works for stars that are relatively close by. So let's summarise. You need to memorise the definition of a parsec. Got to do that, okay? You need to be able to describe the method to determine distance to stars using stellar parallax. So I would, if I were you, familiarise yourself with that diagram that came up over and over again. You need to use D equals 1 over P with the correct units. You can do that, that's simple. And you need to understand that at around distances of 100 parsecs, the parallax angle gets too small to distinguish, and this method no longer works. When you were in, say, chemistry class or early science classes, you may have come across something called a Bunsen burner. And a Bunsen burner is how you heat stuff up in science, right? There's a gas pipe, you light the Bunsen burner with a splint, and you see a flame. And the flame can be yellow or it can be blue. There's different colours of flame. And that flame, the colour of flame, determines how hot the flame is. And it's the same with stars. Let's have a look at this picture of the Sagittarius star cloud. This is us having taken a picture of Sagittarius star cloud with a really fancy telescope. And you can see that not all the stars look the same. They're different sizes. They're different colours as well. And the reason for that is that stars aren't the same. They're not the same because they have different temperatures. So stars with a reddish colour, as you can see there, they are cooler than stars with a bluish colour. Some of the blue stars there as well. So if you have a cool star, it appears red. And if you have a hot star, it appears blue. Now, if we think about the star, it looks like this. It's really hot in the middle, and then it gets less hot as it goes out. So when we're talking about the temperature of the star, we're actually talking about the surface temperature of the star. How hot is it on the surface of the star? So if we see a star that's red, for example that one, it's likely to have a cooler surface temperature. And if we see a star that's bluish, i.e. that one, it's likely to have a hotter surface temperature. So bearing that in mind, we can classify stars in terms of what their colours are. And they are classified with a random series of letters. I don't know why they've chosen these letters. The star here, O, has a surface temperature of 30,000 degrees Kelvin and above. So really hot. And a star that's classified as M has a surface temperature that's 3,000 degrees Kelvin or below. So it's really cool. Our sun has a surface temperature of around about, it has a surface temperature of 5,800 Kelvin. So it sits between this idea of a yellow star and an orange star. So that's why our sun looks kind of yellowy orange, because the surface temperature of our sun is between this idea of a G and K. So if we had to pick one, we'd say that our sun is a star type G and it has a surface temperature closest to 6,000 Kelvin. A star classified as O gives off blue light. A star classified as M gives off red light. The blue light has a lower wavelength than red light. So it's very clear to me that there's a relationship between the temperature of the star and the peak wavelength that star radiates.
And when you plot a graph of the amount of radiation emitted from an object, the intensity of the radiation, and the wavelength of the radiation emitted, you get quite a distinctive curve. Let me talk you through this curve at the moment. Let's have a look at this white star, which is about 5,000 Kelvin, which is not far off the temperature of our star. Our star emits visible light. It also emits some ultraviolet, because that's what gives us sunburn, we know that. And it emits some infrared radiation, because that keeps us warm. So the star emits a range of radiations over a range of wavelengths. But it emits some more than others. So our star would emit more visible light than it would ultraviolet or infrared. And the peak wavelength of that radiation, the wavelength that is most emitted by the star, can be found by looking at this curve. If we look at a hotter star, something that appears blue and is 7,000 Kelvin, the curve has the same distinctive shape. There is a peak radiation, and it does radiate over a range of wavelengths, but it emits more of everything, and the peak wavelength seems to be smaller. If we look at a colder star, the peak wavelength seems to be greater, and it emits radiation over a range of wavelengths, but less of every part of the wavelength. So what this graph shows is that hotter objects radiate peak electromagnetic radiation at smaller wavelengths. And that makes sense to us, because if you look at the blue flame in a Bunsen burner, we know that it's blue, it's got a lower wavelength of light, But we also know that it's hotter. It's hotter than the orange flame. And that tells us a little bit about the astronomical objects. Blue stars are hotter than red stars. On a very basic level, that tells us which star is hotter just by looking at the colour of it. But there is a formula that we can use called Wien's law, and that allows us to find out more specific information. We can work out the wavelength for which the intensity of a star is highest using Wien's law. So we can say the peak wavelength of the star, and if we go back to the graph here, the peak wavelength for this blue star would be around about 450 nanometers, times its temperature in Kelvin is equal to 2.9 times 10 to the minus 3. It's a constant. And the units of the constant are mK. Please don't think that's millikelvin, that is meters Kelvin, because the unit of wavelength is meters and the unit of temperature is Kelvin. What that tells us is as the star gets hotter, the wavelength, the peak wavelength, gets smaller. A hot star or a hot black body will be radiating electromagnetic energy. And the amount that it radiates per second is known as the power, or its luminosity. Anything that's warm will radiate energy per second. And that power can be calculated for a perfect black body. And it's given by the Stefan-Boltzmann law. Once we know the temperature of the black body, or a star, or the Earth, we can use the Stefan-Boltzmann law to work out its total power radiated. So we can work out how much energy, electromagnetic energy, is being released per second using this formula. This is a constant. It's known as a Stefan-Boltzmann constant. It's in your data booklet. This is the surface area of the star, or the Earth, or anything that's radiating energy. And this is the temperature to the power 4. I'm going to highlight again, this formula here is for a perfect black body. So it's something that re-emits all the energy it absorbs. And it also assumes that the radiation from this star, or the Earth, or anything that's radiating the energy, obeys the inverse square law. That means that it radiates out energy in all directions equally, and it continues to infinity.
The Stefan-Boltzmann law gives the luminosity of the star, so it tells you the amount of power that that star is radiating. However, if you're standing a distance from the star, and let's be honest, we all are, then you're not going to feel that same power per unit area because of this inverse square law. You're going to feel less power per unit area, and that's called brightness. The brightness that you'll experience from any star is equal to the luminosity divided by that factor of the 1 over r squared, or the inverse square law. So your formula for the brightness of a star is B equals luminosity divided by 4 pi d squared, which is the surface area of the sphere that surrounds the star at that distance. And d is the distance from the light source to where you're standing. This is another key equation in helping you determine the power of a star, or the distance from the star, or the star's radii. Okay, head to your revision note template, go to the common graph section and draw the intensity wavelength graph. Note where the peak wavelength is, and then beside that graph, note down the following equation. Note down Wien's law, because that's how you actually analyse the graph. Remember, that graph is for a black body, and we assume stars are black bodies. Then go to your common equations graph and write down the Stefan-Boltzmann law and the brightness equation. The last section allowed us to find out the temperature of a star by looking at its colour and its wavelength. We were also able to find out the star's luminosity and its radius using how much power it gives out. The next section, we're going to look at the star's spectra, and we'll find out what the star is made up of by just looking at that spectra.
And what I have here is how many stars? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 spectra from 13 stars. So there's 13 stars here. They've each got their own spectra. And what you can see from these spectra that we've taken out is there's very common lines. All of the stars have a darkish line in the yellow. Can you see that? If you go to all the stars, they've all got a darkish line in the yellow. And they've all got a darkish line in the red part. And they've all got a darkish line, two darkish lines in the sort of the very dark end of the blue. Let's take the darkish line in the yellow, for example. That very thick dark line relates to the very thick dark line in helium. So we can see that most stars have helium in it because that line relates to the helium line. It's called the helium doublet. If we go to hydrogen spectrum, you can see between blue and green, at the very bottom in the hydrogen, between blue and green, you can see there's a thick, dark line there. And if we go to the stars here, certainly the top 11 stars, it seems to have a thick, dark line in between blue and green. So those stars have lots of hydrogen in them. Again, within hydrogen, there's one just at the very end of the orange before it turns into red. There's a thick, dark line. And if you look at all those stars, you can see a thick, dark line. Certainly in the top 11 or 10, there's a thick, dark line which relates to the hydrogen spectrum. So we can look at these spectra from all the 13 different stars, and we can say the top 10 or 11 seem to have lots and lots of hydrogen in them. And then the bottom two seem to have still a bit of hydrogen, but the lines are a bit fainter, but they seem to have more helium. Now, what we know is that what stars do is they burn hydrogen through fusion and it turns into helium. So that means that the bottom two stars, M0 and M5, are older stars because they've burnt most of their hydrogen because the hydrogen spectra is less obvious and it's turned into helium. So because their helium spectrum is more obvious. So we can say they're older stars and we can say the ones above it are the top 10 or 11 stars are younger stars because they seem to have more hydrogen within them. There's also, if you take any one of those spectra and really analysed it, you could go back and have a look at the neon spectra and you can see if there's any neon in that star. You could take the oxygen spectra and you can see if there's any oxygen in that star. The nitrogen spectra and see if there's any nitrogen in the star. These are not clear enough. So what you need are spectra with very, very high resolution, and that's what you get from working in an astrophysics lab.
And I can't quite believe it, but we have come to the very end of the IB Physics course. How amazing does that feel? That has been a journey. It's been a journey for you, and believe me, it's been a journey for me. It's not been easy to record all of these tutorials to make sure they're as clear for you as possible. But please know that I've enjoyed every single second.